right, last section in chapter 9 is permutations and combinations. The first thing we're going to take a look at is the notation. Have you seen the exclamation notation before? Yes. I know a couple of you have, but yes. Got some yeses, that's awesome. Shake no too. All right, exclamation notation, which is always one of those funny math things that we do when people put a number and an exclamation point and say, oh, give me 120, not 5 factorial. This is called a factorial, okay? So what it means is we multiply this number times one number less than that, and one number less than that, and one number less than that, and we keep going all the way down to the number 1. Okay, the shorthanded notation for successive multiplication, one less. Consecutive multiplication. All the way down to the number 1, whole numbers. This is a whole number feature. So we've got, well actually, you would even, well, it is a whole number feature, but it's natural numbers. So if it's a natural number, like 10, I would write out 10 times 9 times 8 times 7 times 6 times 5 times 4 times 1, and then I would stop. I don't keep going after that. I stop with the number 1. And then I would actually multiply all those numbers together. The definition of 0 factorial is that the 0 factorial equals 1. Since it's not something we're trying to prove, it is given as a definition. Okay? It's one of those facts. It's like talking about points. Point has no depth. You can't see it. How can you talk about it? It's kind of one of those weird things, right? But we need it to build upon the other items that we work with when we talk about points. It's the same kind of idea. And you're going to see why the 0 factorial equaling 1 is necessary when we work through this section. We're going to start here with 4 factorial. Volunteer. Kayla. Lauren? Okay, come up here, Kayla. First, write out what this would actually be. Write it all out for me, okay? Excellent. So this is equal to 4 times 3 times 2 times 1. And then you're actually going to multiply. So 4 times 3 is 12 times 2 is 24. And do we really need to care about what times 1? No. We're at 24. You're done. Thank you. This is what factorials do. It's just a shorthand notation for multiplication all the way down to 1. And that's really all it is. Okay? So let's take a look at one more feature, and this is actually from chapter 2. I don't do a lot of this in Math 1, although I know some of you had Math 1, and we talked about this a little bit, but not a lot. It really comes into play in this particular section. Like if I were writing the book, I would have put it here. I wouldn't have put it back in chapter 2. But here's the deal. This is called the fundamental principle of counting. If you have an event M, capital M, and it can occur in M ways, and you have an event capital N, and it can occur in little n ways, then the number of ways that the event M followed by the event N can occur is M times N. And all of that sounded kind of funny until we do an example, and you're going to go, oh yeah. Okay, here's the deal. Pizza Planet. Where's Pizza Planet? It's a Toy Story. Every now and then my son says he wants to go to Pizza Planet. Did you know that there is a Pizza Planet in Oklahoma City? No. Well, the reason I know is because it came from one of those deal sites. You know, like Groupon or something. I didn't get one, but I did notice and I laughed. All right, Pizza Planet. Pizza Planet offers 3 kinds of salad, 15 kinds, not kids, 15 kinds, little scary, 15 kinds of pizza and 4 desserts. How many different meals consist of 1 salad, 1 pizza, 1 dessert? So, what the fundamental principle of counting does for us is it allows us to see how we would put this all together. So the first thing is my salad. How many different kinds of salad do we have? 3. Then I've got my pizza. How many different kinds of pizza? 15. And then I've got my dessert. And how many different kinds of dessert? 4. And what the fundamental principle of counting says is I just multiply the factors together, and I'll find out the number of different meal combinations that I could have. Okay? What do we get? What is 3 times 15 times 4? 480? 180. 180. Okay, sorry. 180 different meals. A couple of years ago, Sonic came out with a slogan or campaign or whatever you would say, and they've got over 1 million different drink combinations. You guys know that? This is how they're doing that, okay? But theirs is a little more complicated because you can add in 1 flavor or 2 flavors or 3 flavors. Eventually it becomes cost effective, right? Because they keep charging you for the extra flavors unless you're that's not going to charge you. But this is how they do that, okay? So they are figuring out with different combinations like this. This is what they're doing. And a little bit further into that idea is what we're going to encounter next. Okay. Permutations. I also know that some of you have seen this before. Permutations are ways of choosing objects. And that's what it is. It's the number of ways of choosing an object. So notationally, it looks like this. So the N and the R look like subscripts. They look sort of like down below the line a little bit. And the P is just the fat old P on the line. Regular P. P for permutation. The N is the number of items you're picking from, and the R is the way to pick, is the number of items you're going to pick. So for instance, back at Pizza Planet, let's say that you got to choose 3 of the kinds of pizza. Right? It's like a buffet, you know, like you go to Mazio's or something like that. You could pick from the pizzas, and you chose 3 of the 15 different kinds of pizza. Well, how many ways could you pick the 15? Well, one of the things that will come into play here is whether or not the order matters. If it's a permutation, the order matters. This is in red, it's big, bad, bold, and you need to make sure that you highlight, circle something to tell you, because this is the kicker. All right, so with my pizza example, probably didn't matter. If I picked 3 pieces of pizza and I put them all on my plate, I've got 3 different kinds of pizzas, right? And it really doesn't even matter what order I eat them in. That doesn't change what I ate. Okay, and the net result is I still had 3 different kinds of pizza, and the order didn't matter. But there are some things in which the order does matter. So we're going to do this example in a minute, but let me give you another example just to kind of think of the order mattering versus order not mattering. So was it last summer we had Olympics or 2 summers ago? Last summer's Olympics, okay. So up to the point when you get into the Olympics, they have qualifying rounds. Everybody knows what that's talking about. And I don't even mean the ones you see on TV, but I mean like when the U.S. decides who to send for the gymnastics, there's qualifying rounds. And it doesn't so much matter that you're the first place in the qualifying round. You just have to be in the top 3 or the top 5 or something like that, right? It doesn't matter if you're first, but it matters that you got in. Okay? And the same thing happens, this is another random example, but does anybody watch Biggest Loser? I don't know, the one that they talked about this week, one of the gals said they lost too much weight last week because the goal should be to lose just the very bare minimum to stay in the game so that the next week you could lose more. Okay, bare minimum to stay in. So this is kind of like the idea that the order doesn't matter, you just got to make the cut. Okay, qualifying rounds, we don't care, we just want to get in. Kind of like the playoffs right now. I'm full of examples today. Kind of like the playoffs with the NBA stuff right now, not NBA, NCAA, the basketball stuff, right? You know, everybody doing these tournament championship brackets. There's one going on campus. Did you know that? Yeah, it's free to enter if you're interested. What's the guy's name that they would contact? David Gardner. Thank you. So anyway, it doesn't really, I mean, it does matter to some extent where you're placed in the bracket. But what really matters to most teams is to get in, right? Because there's always those teams that are sort of on the bubble. That's the language, right? On the what? They're really close to getting in or not getting in. Okay? So anyway, but if you get in, you get to be in the tournament. And then you have a chance at the final championship. If you don't get in, you don't have any chances. Okay? Then, once you're actually into the Olympics, then it matters because first place gets a different prize than third place. And if you're fourth place, you get nothing. Okay? So once you're actually into the tournament, once you're actually into the final whatever it is, then the order matters. Then you're in a permutation combination, a permutation situation. All right. 50 people show up for a game show. 2 people will be selected at random to participate. How many different ways can this happen if the order matters? So sometimes in a problem, they will tell you the order matters. And sometimes you get to make that decision on your own. And I don't mean like there is really a decision. You have to figure out which one it is. That's what I mean. Like you have to read it and decide. So this one they tell you, order matters, right? So because the order matters, we're using a permutation. How many people or things are we picking from? 50. And how many are we choosing? 2. All right, so now I need to tell you what we do with the 50 and the 2. So let me go back up to the description above where I was writing the formula and then I stopped. NPR is n factorial over n minus r factorial. P, the R occurs after the P. Also, just FYI, the N's always bigger than the R. So when you're subtracting, big minus small, you're in good shape. Okay. All right, so what goes on top on this one? 50 factorial. What goes on bottom? Yeah, 48, 50 minus 2, 48 factorial. Now, a couple of things. So I'm going to borrow Orion's calculator for a second. If you have a calculator like this, the TI 80, 283, 85, 86, these kind of calculators, they have the keys that will let you do some of this to help you out with factorials and things like that. And you can use that to check your work. Let me show you what work I expect to see, though, that you have checked. All right, one kicker, though, is that if you type into your calculator, I'm not sure if 50 is large enough, try for me more. Can you do 50 factorial? Can I do it? Ah, good. That's exactly what I wanted to know. All right. So if you type in 50 factorial into your calculator like Warren did, it's going to come up 3.04. Does that sound reasonable to you? No. And if you look at the ends, there's why. It says capital E 64. Do you know what capital E means in your calculator?
It's like
Scientific notation, and Kayla's drawing pictures in the air. It means times 10. It means times 10 to the power, in this case, 64. So 50 factorial is 3.04140932 times 10 to the 64. And I probably missed some decimals because the calculator simply doesn't display all of them. Okay? So this is really not a helpful notation for your calculator to deal with. So let's figure out how we can make the calculator give us something that makes sense. I'll show you. All right, so what is 50 factorial? What does it mean?
it's 50 times 49 times 48.
Okay. What does 48 factorial mean? Do you see some simplifying in terms of fractions that you could do? Yeah, you can get rid of 48 all the way down because they match, right? These all match. So let me show a shorthand of how you can do this instead. Some of you are already saying it because you've taken this before with me. Not this class, but this content. So with the 50 factorial over 48 factorial, what you can do is you can write out the 50 until you get to the 48. Now you can't cancel out 48 with 48, but you can cancel out the entire 48 factorial with the entire 48 factorial. And to be honest, your calculator is going to be much happier, and so are you, because you can do 50 times 49 pretty quick. And what do you get? 1,000 what, Lauren? All right. So if we're selecting two candidates to play on the game show, two contestants, there are, out of 50, there are 2,450 different combinations, I'm sorry, I used the word wrong, different permutations, different ways in which we can select them, if the order matters. Now, order doesn't always matter. So we'll get to that one in a minute. But let me talk one more time about permutations. Sometimes when you do permutations, you get things mixed up. And that's not the right word I'm going to say. It doesn't matter some of what the order is. So let's, for instance, give an example. If you had a bag of Skittles, and you reached in and you pulled out a red Skittle, would it matter if I pulled out the red Skittle that was at the top of the bag or the bottom of the bag? No, it would still taste like a red Skittle, right? So there's some sort of a distinguishability. I can't distinguish between red Skittle number 1 and red Skittle number 5. That's what's going on with this set of permutations. In this permutation, we've got some objects that match. Okay, so my best examples are all about candy. I don't know why. M&Ms, Skittles, peanut M&Ms, peanut butter M&Ms. We could do all kinds of M&Ms. Jelly beans, I'm not sure Reese's. You can do Reese's peanut, but like a Reese's Pieces would work. I think I've done a Reese's Pieces example before. Yeah, I think so. Yeah, so candy works really well. We're going to do an example that's not candy, but if you have indistinguishable objects, so permutations where there are like objects. Okay, so the last example didn't have that, right? Because we had people. Even if they're twins, they're not the same person. Okay, so that's not going on in the last example. But here, we're talking about candy, or this example we're about to hear, that's when this matters. So the way that we do this kind of a permutation is it's n factorial on top, just like the other one. Okay? But instead of dividing by n minus r factorial, we divide by r1 factorial, r2 factorial, r3 factorial, all the way way till we get to whatever we have, however many different indistinguishable objects we have. So if we were talking, let's do M&Ms. How many colors M&Ms are there? There's red, blue, orange, brown, green, yellow. I think that's right. So there's 6 of them. Okay, so what we would have on the bottom is we would have 6 different things with factorial on them. One for each of the different colors based on how many of each of them there are. So if there's 5 browns, we'd have a 5 factorial. If there was 3 reds, we'd have a 3 factorial. If there were 2 yellows, we'd have a 2 factorial, and so on down the line. Okay, so that's how that works. We're going to do the same thing for this one right here. How many ways can you arrange the letters in the word Tallahassee? As you can see, some of the letters repeat. So what we're going to do first is we're going to figure out what letters we have and how many of them we have. There's 1 T. What's next? How many A's? 4. 3. 3. Wow. How about L? 2. Next letter is H. There's 1. And then what? S. And there's 2. All right. So how many letters do we have total? 11. We need that value because that's my numerator. Okay, so I've got 11 factorial on top. And then I'm going to divide by each one of these numbers that I wrote out with a factorial on it. So I'm going to have 1 factorial, 3 factorial, 2 factorial, 1 factorial, 2 factorial, 2 factorial, and I'll be done. Things don't cancel out quite as quickly as last time, right? I had 50, 49, 48, they all canceled. Okay? Here, I'm going to have to go down to all the way to 3 factorial before it finally cancels, but I'll still get something to cancel. So 11, 10, 9, 8, 7, 6, 5, 4, and then 3 factorial. Now, the 1 factorials, do I care? No, because they're just 1, so ignore them. They don't really matter. We've got the 3 factorial that we'll cancel here in a minute. And then what is 2 factorial? 2 times 2 times 2. All right. So what cancels? 3 factorial cancels.
Wait, where did you
The 2 factorials. Because 2 factorials is 2 times 1.
2.
You could cancel 2 the 2's with 4. What else could you do?
Do all of them with 8.
You could do all of them with 8. Either way, it's going to give you the same result when you're done. So what we're looking at now is taking our calculator and multiplying 11, 10, 9, 7, 6, 5, and 4. 11 times 10 times 9 times 7 times 6 times 5 times 4.
Why don't we have two?
Say again? Oh, because I stopped at the 3 factorial, because once I have the 3 factorial, it matches this 3 factorial and can be reduced. I mean, I could write it out the whole, but it's just simpler once I get to one that matches to stop writing. On this one, it's all silly because these numbers, at the point I got 3, it's just 3 times 2, like I said. But on the previous problem where I had 48, it was very helpful. So I didn't have to write out 48, 47, 46, 45, all of that out because they already matched. Did we get somebody else to match the number? Excellent. Make sense? Okay, so again, this is when order matters, the different order. Sometimes order doesn't matter. And when order doesn't matter, again, star flag, make yourself very aware that the key to this whole idea is that order does not matter. When order does not matter, you've got a combination. And when you've got a combination, you've got what Sonic does. Because it doesn't matter if Sonic puts the strawberry in my drink first or the vanilla in my drink first, I still have strawberry vanilla Diet Coke. Okay? So that's what's going on when you're talking about something where you're adding something in like that. If you went to the pizza buffet, like I was saying, right, it doesn't matter if I get a pepperoni and cheese and a sausage, I've got one of each, I'm probably going to eat them all, it doesn't even matter what order I eat them in, they all went into my stomach. Alright, so let's take a look at what this one looks like. This is in CR. C for combination. Formula looks much like the permutation formula, n factorial over, and I've got an n minus r factorial on the bottom. The difference is that I've got an additional r factorial. So in general, will this number be bigger or smaller than the same equivalent permutation? Smaller, because I'm dividing by more, right? I'm dividing by something else, it's going to be additional. So this is going to be a smaller number. And the reason is because if order doesn't matter, there are fewer ways that something can happen. Make sense? Okay, let's try one. Again, 50 people showed for the game show. 2 of them are selected at random to participate. How many different ways can this happen if the order does not matter? All right. So I've still got the 50. I am doing a C now with 2. I still have 50 factorial on top. What's on bottom on this one? 48 factorial because it's 50 minus 2, and 2 factorial because I've now got the r factorial on bottom. The process for doing it, same thing as before. I'm going to write 50 times 49 times 48, and I'm going to stop with 48 factorial to match the 48 factorial on bottom. And then I'm going to have 2 times 1, and the 48 factorials are going to cancel. Then what will I do? Yeah, I'd reduce the 50 and the 25 because it happens pretty quick, and I don't have to have as large a number for my calculator to deal with. So now I have 25 times 49. 1025? 225? Good, that's what I have too. Good. All right, so there's actually in this particular case half the number of ways. And that should make sense, because if you're just selecting 2 candidates to play the game show, and it doesn't matter, then I don't have to have the other operation, right? The one where it says you were first and you were second, now you're first and you're second. It doesn't matter anymore. All right, so we're going to take a look at some different things. These are going to be different random problems. Now, some of them order matters, some of them doesn't. We're just going to have to read the problem and figure the things out, okay? So, if all phone numbers on campus are 405, 858, and there's 4 digits after that, how many different phone numbers are possible? So, some of these are going to use permutations, some of these are going to use combinations, some of these are going to use fundamental principles of counting, and some of them are going to use a multitude of things at the same time, okay? So taking a look, we've got 4 numbers at the end. How many different possibilities are there for each of those digits? 10. What numbers are they? 0 through 9. There are 10 different one-digit numbers, right? 0 through 9. Can I repeat digits? Yeah, I mean, phone numbers work that way. I can repeat the digit, doesn't hurt anything. So there are 10 ways I can get the numbers 0 through 9 for each of these places, correct? And then this one is actually a fundamental principle counting problem. Because what I'm going to do with these numbers? Multiply them all together. Kind of like along the trees of a branch of a tree diagram, actually. What number is this? 10,000. I think an OBU would be okay with the 10,000 numbers. Probably okay, right? Or maybe not. Who knows? 10,000 numbers anyway. So we have 10,000 numbers possible. All right, a worship team practices 8 songs on Sunday night for the Sunday service. If the minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? So, what kind of problem is this? Is it a combination?
How many ways can the songs occur?
Okay, so what do you think? Think order matters? I think so too. You guys have been in services before where it seemed like, man, that slow song in the middle of all this fast songs is really weird, right? Sometimes the worship ministers don't do such a good job of doing this, and most of the time, though, they do. They think about that, right? They think about the pace of what's going on, or the volume of what's going on, or the structure, or maybe they really want the hymn right before the prayer time. I mean, the order is an important thing. It's one of the most important things when they're thinking about structuring the songs, not thinking about choosing the songs. They would think about structuring them. All right, so we're going to do a permutation because the order does matter in this case. Okay? So how many am I choosing from? 8. I'm using a permutation, and how many am I choosing? 5. All right, so what will this look like? I want to hear, somebody can come up here. Who wants to come up? You want to come up this time, Lauren? Thank you. Lauren doesn't have to do the problem by herself. You guys are going to help her. What's she going to put on top?
8.
Okay, what goes on bottom?
5. 3.
I mean 3 factorial.
3. Okay, good. Now what does she need to do?
8 times 7 times 6 times 5 times 4 times
3 factorial.
And?
over 3
And then it's cancel out.
So great.
Okay, Bailey's got a calculator. She's going to help us out. Bailey, you have 8 times 7 times 6 times 5 times 4.
6,700.
Yeah. Look good? Awesome. Thank you, Lauren.
Good job.
Okay. Next one, we're going to do 52 card deck. We've talked about card decks, right? Okay. So we're back to the same idea. All right. Here's the deal. We've got 52 cards, and we're going to be dealt 5 cards. So card games often will have a certain number of cards dealt to each player. That's what's going on. We're dealing 5 cards to whoever. How many different 5-card hands are possible?
Order doesn't matter.
Order doesn't matter. Why?
It's just how many, like, say like, the order of them, just 5 cards.
Okay, so use what you know about card games. Why does the order not matter?
That's not going to change anything if you're 2 and your hand is 4.
Right. In fact, usually what we do, at least I do, when I get a card hand of whatever game we're playing, even if it's like Uno, the first thing you do is you reorder them, don't you? You put all the blues together, or put all the kings together, you put all, whatever the card game is, you restructure it in a way that makes sense for that card game. Maybe it's in the order of increasing numbers, or I don't know, it depends. But it doesn't make any difference whether you got the ace first or the ace last, or going outside of that kind of card game, the wild card first or the wild card last, right? Okay, so this is definitely a combination. Combination of what? 52, C5. All right, so what's going to go on top? And on bottom? Okay, remind us again where the 47 comes from? 52 minus 5, good. Now, and this is where these factorials are really handy because I don't want to write out 52 all the way down. When I have large numbers, it becomes cumbersome to deal with them in that way. But I can write the 52 out till I get to 47, okay? And then I'm going to write 5 out as well. 5 times 4 times 3 times 2 times 1. All right, so first, rule of thumb, mark out my factorial. All right, let me give you a couple of other kind of tidbits of information. When you get to this point, everything in the denominator has to reduce with something in the numerator. I mean, like completely. We should be able to completely eliminate the denominator. You will always end up with a whole number when you're done with this thing. So if you ever end up with a fraction, there's an error, go back, find it. Okay, end up with a decimal, find the error. All right, so what would you like to cancel? There's lots of ways to do it. 48 and 3. Okay, so 48 divided by 3 is what? 16. Now what?
Divided by 2.
Okay, 16 by 2?
Or 4.
We could do the 16 by 2. What if I do 16 by 2? I have 8.
Well, then right.
Oh, you want to divide by 4 next? Okay, so then divide the 8 by 4 and I get 2.
And then 5 and
5 and 50, and then 50 becomes a 10. So you're going to take your calculator, you're going to multiply 52, 51, 10, 49, and 2. Don't lose track of the new number you changed it to. And how many do you get?
5,
Yeah.
I believe so. Good. All right. Let's try a couple others that are about this hand of cards. How many different 5-card hands would have all diamonds? What would you have to do for that?
Change the number that you would choose from.
Change the number you can choose from. Who's going to volunteer for me? Everybody's going to tell you what you have to write. You don't have to do that. Great. All right, so Kayla says she wants to change how many she's choosing from. Why are we changing how many we're choosing from?
Because you want all diamonds.
Because we only want diamonds now. So we don't have the whole 52 cards that we can pick from to make this happen. How many do we have? 13. So we're going to pick from 13. How many are we going to pick? 5. Good. All right, so what's he going to write next?
13 factorial. 8 factorial. 5.
How did I get the 8 factorial?
13 minus 2.
Good. Grant, that was fabulous. All right, now what's he going to do?
Write up 13 times 12 all the way to 8.
Right. Okay, and then he's going to write the 5 out as well, right? 5 factorial, all of it's written out. Okay, we can take away the 8 factorial, right, Grant? Okay. What do you guys want him to take away next?
5 and 2 with 10.
5 and 2 make 10. They're multiplied anyway. Yeah. Now what else?
4 and 3 is 12.
4 times 3 is 12. Very good. So we end up with 1,286. Does that look okay to everybody? I have 87.
I got 87.
I have
Okay.
87.
Oh, I changed it to 7. That's okay. I don't think it should be even because we aren't having a number upstairs anymore. Awesome. Thank you. Who wants to do the next one? Who wants to do the next one? You get one participants, remember, audience participation. Do I have to volunteer somebody?
I'll do it.
All right, Maggie, come join us. I'm going to start putting your names in the hat and drafting.
And then we're gonna have to figure out the probability of who is gonna get picked. It's just gonna be a mess.
That's right. All right, probability of getting a 5-card hand of all diamonds. How many do you guys need?
So you just, let's say go 5 out of 13.
Oh, I don't think it's written quite right. That's what's wrong. I was thinking about something else. Oh, no, it's fine. That's what's wrong. What's the difference between what this is written as part A, part B? It's got a probability. Circle the word probability for me, Megan. How do you figure out probabilities? There you go. Part B was the number of ways of getting a hand of all diamonds, right? The 1287. Part A was the number of ways of getting any kind of hand. So we do the answer from part B. That's your 1287. Over your answer from part A, which was
60.
okay, so you can either reduce it in fraction form or you can turn it into decimals. I don't care. If you choose to change it into decimals, let's go with 4 decimal places. 4 or 5. Go around. Yeah. Okay, so 0.0005. Thank you, Nate. All right, so what we did here. What we did here is the probability of getting all diamonds. It's not probability, the number of ways of getting all diamonds. Or the number of all diamond hands divided by the number of total hands possible. sense? This is actually called a diamond flush, just so you know. So if you ever heard something about flush, it just means all the same soup. This is soup diamonds. Is that very likely?
No.
It's a pretty small probability, right? That's less than a 1% chance, because 1% chance would have a 1 right here. Okay? All right, let's try another one. A committee is selected, a committee of 3 people is selected at random from seniors, juniors, and sophomores. 7 seniors, 5 juniors, 3 sophomores specifically. What is the probability that the committee consists of all, what do I have first? Seniors. So what this is doing, first of all, to recognize is it's doing what the last problem did, part C of the last problem. But it's doing it so that you were not led into it by doing a part A and a part B. Okay? So in order to find a probability of all the seniors, I would need to know the number of all senior committees divided by the number of all committees. That's what I did in the last slide, right? The number of this divided by the number of that. How do I find the number of all senior committees?
The probability, or the
It is, and it is a combination because the committee, the order doesn't matter again. You're selected first, you're selected last, you're still the other committee. So how many seniors are there? 7. And how many are on my committee? 3. So there's 7C3. There are 7 people I'm picking from. 3 of them are going to get picked if I make the committee all seniors. But how many people am I actually picking from the total number of possibilities? 15, because I have 7 seniors, 5 juniors, and 3 sophomores. So there's 15 people. So I have 15 people that I'm selecting from, and I'm still selecting 3 of them. All right, so my suggestion then is let's kind of do this as a side piece of work. We'll find each of those numbers and then we'll divide them, kind of like we did on part A and B before. So we're going to create our own A and B, and this is going to be part C. So part A is going to be me finding 7C3. So what's that going to be? Over 4 factorial, 3 factorial. So the 7 I will write out until I get down to 4. The 4 factorial can stay on bottom, and then the 3 is 3 times 2. What's going to reduce? 4 factorial,
And 6.
and 3 times 2 is 6, so this is 35. So there are 35 different committees that are all seniors. Part B, my made-up part B, is the 15C3. What's that going to look like? 15 factorial over 12. Okay, so the 15, 14, 13, 12 factorial, I get a stop. And then, oops, I still have a 2 there, I don't know why I'm 3 factorial at the bottom. And then I have 3, 2, 1. What reduces?
Just the 12.
12 factorial reduces, what else?
3 and
3 and 15, make 15 become a 5.
2 and 14.
2 and 14, make the 14 become a 7. So we actually have 5 times 7 times 13, which is 455. So I got the value that I needed for the denominator, 455, and then your calculator can take 35 divided by 455. And let's go with a decimal to 4 decimal places. So that's my answer with all the pieces below. Make sense? Okay, let's take a look at the next problem. This one says, what's the probability the committee has no seniors? Okay, not that it has not all seniors, because if it had not all seniors, we could just do 1 minus the last problem, right? That would mean that there's at least, somebody else in the committee. That's not the problem we're asking here. No seniors. Okay, so Whitney, tell me what you want to do, because I heard your voice first. Okay, so what you're wanting me to do then is to find the number of no senior committees over the number of committees, right? And because there are 8 kids that are not seniors, I'm going to choose from that 8 to choose 3. The denominator should be the same though, right? So if you've already done one part of this problem, don't do it again. 455, we already did that. But I need to do, if you will, a part A down here, right, that's 8C3. What will that look like? So hopefully you've already noticed this, that the 2 numbers in the denominator add to the one in the numerator. Okay, real quick, make sure that you didn't write something down wrong kind of thing. Yeah. All right, then we're going to write down 8, 7, 6, 5 factorial. Over 5 factorial, and then 3, 2, 1. What reduces?
5.
5 factorial,
And the 3 times 2 is 6.
and then 3 times 2 is 6. What do I have left? What is it?
56.
56, good. So this is 56 divided by 455. 0.1231. So it is slightly more likely to have no seniors on the committee than it is to have all seniors on the committee, right? But it's still not very likely. I mean, that's 12% chance. Yeah. Most likely we're going to have at least one senior on there. We're going to have some combination of these things.